All right, everybody, we're going to go ahead and finish up chapter 9 here. We are now going to compare two variances, actually two standard deviations. We're not going to do variance. Two standard deviations as we look at this. And the requirements are the two populations need to be independent. The two samples are simple random. And each of the two populations, they have to be normally distributed. Again, anytime we're analyzing standard deviations, it has to come from a normally distributed population. We're going to use something called an F-test. And that's new for us. And this is going to be the standard deviations squared over one another. And S sub 1 is the larger of the two. Standard deviations. And we're going to just jump right down into it. And so this one has degrees of freedom, and I'll say for the numerator is n sub 1 minus 1. Again, n sub 1 is the larger of the two. Degrees of freedom for the denominator, sorry, I'm a little off track here. For the denominator are going to be n sub 2 minus 1. And again, n sub 2 is the smaller of the two population sizes. And we are going to move on to our example here. And we're going to use this data to determine the difference in standard deviations between body temperatures between men and women. And here we have the information. Now, they give us a 0.05 significance level. Let's write our null hypothesis. Once again, we're going to assume that all things are equal. And the question actually says that it varies more than, so this means sigma sub 1 is bigger than sigma sub 2. Again, which will make this right-tailed. Now, an F-test looks very similar to a chi-squared test, meaning the graphs are very similar. And we start at 0 with these. And because it's a left-tailed test, because it's larger than, this should be a right-tailed test, pardon me, right-tailed test. We are here. And we are just going to compare p-value to alpha level for this. And for our test statistic, which is this F up here, we have a program that we can do this. So if I go into stat and I go to tests, we're going to have to go way down for this one to a 2-sample F test. And you can see I've already put the data in here. N is 11, 0.66, and 59. And it's going to be larger than. When I calculate it, it's going to give me that. Now, I could have done this squared divided by this squared, and I should get the same F. I'll verify that here in just a second. So our test statistic is about 1.818, and our p-value is 0.0774 about. Let me, again, just show you real quick. If I took 0.89 squared divided by 0.66 squared, again, you can see I end up with the same F value as we're looking at that. But very nicely it gets us the p-value, and this p-value is distinctly larger than our alpha, which is 0.05. So we are going to fail to reject. The null hypothesis. So there is not sufficient evidence to support the claim that men's temperature standard deviation is bigger than women's. Let's do one more. Test a claim that those who tested with a red background have creativity scores with a standard deviation equal to that of the standard deviation of those tested with a blue background. And we're testing this. Sigma sub 1 is equal to sigma sub 2, or that it's not equal to. Which means it's going to be a two-tailed test. And you can see our significance level here is 0.05. Gets split up. It's hard to find the critical values with these. We have to look things up on tables, and if you look up F distribution table on the internet and hit go, these are just pages and pages and pages long, which is why I'm doing the p-value versus the alpha test. So let's clarify. This is 0.025. 0.025. Some teachers do have you do that, but I'm not. So I'm going to run the F test to get our test statistics. So stat tests, and I'm going to go up. I think it's a little faster. 2 sample F test. And our first standard deviation is 0.97. N is 35. And 0.63, and N is 36. And this is a not equal to. And this gives us our test statistic of F is about equal to 2.37, and our p-value is 0.0129, which is less than our alpha. So in this case, we are going to reject the null hypothesis. And again, I've forced this to be the claim, even though it isn't quite worded that way. There's sufficient evidence to support the claim that the standard deviations are not the same.